Okay, yesterday we stopped at this example 3. So what we have learned last lecture is that we learned the level rules, right? We calculate how many percent of liquid, how many percent is solid by using the ratio, the ratio. Okay. Now, today we learn non-equilibrium. Non-equilibrium, when the state of equilibrium is never completely achieved because the rate of approach is extremely low. So when the rate of approach to equilibrium is extremely low, we say that the system is non-equilibrium or meta-state. Okay. So since atomic diffusion is very, very slow in solid states, so they need some time for them to eliminate the concentration gradient. So you will see some microstructure like this one, you see like of the metals. So you'll see that the core structure and so on. Okay. So how the curve structure form that you see on the screen here. Okay. So we're going to look at phase diagram again. So if you look at this diagram is nickel and copper. Okay, nickel and copper. So first you look at the diagram. The y-axis is temperature. X-axis is the ingredient. So here 100% nickel. So here is 30%. So as you move on, then you have more copper. Okay. Okay. So what you can see here is you have the blue line that we very familiar yesterday. The blue line. Okay. So blue line, you see that this is liquid. This is solid. Alpha is a solid, right? So this one, when it transition from liquid, touch the line, you will see liquid, then chicken pox come up, like a solid particle come up. Then it go into grow bigger alpha in the middle section here. Then it pass through this one, means you already reach very little liquid and lots of alpha. Once it pass this border, you have 100% alpha, solid. Okay, so at this line, they still have liquid, but maybe 1%, 0.01%. You still have liquid, but very less. Okay, this one, right? Okay, this one I'm going to explain. So yesterday we are having equilibrium state. Now we're having inequilibrium. Non-equilibrium state means it's not enough time to cool down. Means it's rapid cooling. It cool very fast. That it's not enough to reach the. So as you can see here, the line here, the blue line here, is towards the solid side. As you drop the temperature, you see the temperature gradient drop very, very fast compared to this one. Okay. So yesterday we are in equilibrium. Now we look at non-equilibrium where we cool down the metals very, very fast. Okay. So we try to capture what happened at a certain things. So for example, we consider 70% nickel, 30% copper, which is at this line. You draw the X line. So 30% copper, 70% nickel. Is cooled from a temperature T0 at a rapid rate. Okay. So this is a composition of copper nickel, and it's a bit different because we flip the graph. We flip the graph. Actually, it's the same experiment but different presentation. I hope you can see the similarity and differences. It's the same graph for nickel and copper. It just flip the side. Okay, it's the same component, but it's just that on the left is copper, on the right is nickel. In this case, on the left-hand side graph, nickel is on the left, copper is on the right. That's why the whole graph, the red color graph, flip into the left-hand side. Yeah. So again, what is important that you know at what zone you have liquid, what zone you have solid, and what zone you have liquid and solid. That's more important. Then you know how to draw the level rules, like the tie line. Okay, now I just want to highlight lah. Actually, it's the same things, right? So we are having this section. We flip the graph. We only flip the graph, but it's the same process. Okay. Now let's look at what happened to the when it cool down. When you cool down from T0, very high pressure temperature above 1455 degrees C, you drop down to a certain degree. So you see, when you drop down here, when you drop temperature from T0, now the question will ask you, at what temperature the first solid will form? Here. So when you drop at, if your solution having 30% copper, you start from X and then you drop temperature from here to here. Okay, so you touch this line, right? But this line is what? This line is liquid and solid. Then this one is liquid, solid, solid. This one solid, liquid, solid, liquid. Then one is solid. So this one, So at first solid form at temperature T1 and has composition of alpha 1. Okay, composition alpha 1 means when you drop at this temperature, you reach this one, right? So here you have 100%, you can say 100% liquid if you want. And you have how many? You have 30% copper, 70% nickel. Okay, but in this case, if you do another line at this temperature, you draw a line at this temperature. So this line is what? This one is, you can say like 100% solid already. Okay, so at 100% solid, what is the composition? About there lah. That means it's not no longer 30% composition. It's here. Yeah. Right. So you have alpha 1 composition. Then you further rapid cooling to T2. You further drop to T2. Drop to T2, you have second composition. Okay. Additional layer of composition alpha 2 will be formed without much changes in the composition of solid primary solidified. So here, you drop to T2, you flip to another one, you see a composition of alpha, comma, and alpha 2. There are two composition. One is equilibrium. Equilibrium means you cool down the hot metal liquid very slowly. The black color one is you rapid cooling. Okay, so you'll get solid faster than the normal cooling. Okay. Okay. So the composition of alpha 1, when you cool down, you have up another layer. The another layer outside alpha 1. You will see alpha 2. Okay, it's like coating lah. Another layer, another layer. So you will see at temperature number 2, T2 here, temperature 2, you will see two layer. You will see two layer, alpha 1 and alpha 2. Okay. And as you drop further, you have more and more layer lah. Okay. Each layer have your own composition. Right. So here at T2 you have alpha, comma, alpha, comma. Means this is rapid cooling. Okay, rapid cooling. Only rapid cooling you can see this one. I think the notation for my graph here, diagram here is a bit wrong. You should see comma. Alpha, comma, alpha, comma. Okay. Okay. So overall composition at T2 lies somewhere between overall composition of T2 is lie between alpha 1, alpha 2, and will be designed as alpha 1. So it will be between these two dots, alpha 1, alpha 2, but alpha comma will be a bit higher than alpha 2. So we denote as alpha comma 2. So since the timeline alpha comma L2 is longer than alpha 2 L2, you see this one. If you look at this line, yesterday what we learned is from here to here, right? LOS. But now if you do rapid cooling, the line is a bit longer, alpha prime 2 here, a bit longer. Yeah, and play the black line. So it's a bit longer. Okay, so they will be more liquid, less solid in rapid cool alloy. You know how to calculate LOS, right? Okay, so how this statement do? Okay, recap yesterday. Let's say we have two lines, and you draw the line, right? This is your X. O. Let's say this is liquid line. This is solid. This is L plus solid. Right? So where is your L? L is here. LOS. Right? How you calculate percentage of liquid? So if you want to find percentage of liquid, you find here, divide by the total length. So SO and divide by LS lah. The total length lah, correct? Okay. Percentage of solid, you just take 100% minus this one lah. Or you can take this one, divide by this one, same. Okay. So now, what happened in this slide is that now you rapid cooling. Point become here already. So this one longer. It just means this one longer. So if this one longer, the percentage of liquid will be longer, right? So SO plus delta something lah. Here is delta. Divided by LS also lah. LS plus this one lah. But the percentage will be a bit more. The percentage will be a bit more compared to the normal cooling. And this is it means this one. So they will be more liquid and less liquid in the rapid cool scenario compared to a normal cooling with its equilibrium process. Right? So solidification have been delayed at temperature by the rapid cooling. So it means because here you have more liquid percentage when you do rapid cooling. So inside the crystal, you will see some liquid there. It's like ice cube inside there. You see still got water inside. Okay. Okay. So here, as a temperature lower to T3 to T7, the same process happen. Follow the non-equilibrium solidus line. So the black color line lah. Okay. So means if you follow this line, you have more and more liquid percentage in the metal. It means in the solid metals. Okay. Can so this is the thing lah. Okay, so you will see more and more layer if you cool it down. Rapid cooling, this one happen in rapid cooling only. Okay, so if you're normal cooling, you only see one type of material lah. Okay, okay. So T6 at T6, solid freezing has less copper than the original composition of alloy, which is 30%. So T6 here, if you pull now, you will see less than 30%. Okay, it's mean lah. Okay, temperature T7, you reach here. Average composition, it will be 30%. And the freezing is complete. So when you reach here, you mark here. So the freezing, when it reach 30%, is consider freezing process complete. It's not that no more, they still have, if you follow this line, it means, yeah, you can say no liquid, 100% solid, but the composition, it meet to original one, 30%. So means from 30% here, 30% copper, you rapid cool until 30% at this temperature. Okay, because you further cool, this line going to go here already. This black line going to go here. The percentage of copper will be increased. Okay, so it's like you want to make a type of metals with a certain percentage. Let's say you want to pour in a liquid. This is a hot liquid. Let's say 30% copper, 70% nickel. This one at, let's say, 1500 degrees C. This one is in liquid, you know that at this temperature is at liquid, right? When we do rapid cooling, we want to get solid 30% copper and 70% copper. You rapid cooling until temperature T7. Then you get the same composition, solid. Okay. Now, if you do a normal cooling without rapid cooling, if you want to still get 30%, you need to stop at around T5 and not T7. Understand? So if a normal one, you need to stop at T5, around T5 lah, around. Then you get the composition, 30% copper, 70% nickel. So this is a difference between normal cooling and rapid cooling. You straight away, you drop the gradient of the temperature until very, very low. Then you get the products you want. Okay. Okay, you want to eliminate this core structure. Okay, you get this core structure because you do rapid cooling, and you want to eliminate this one. Okay, to eliminate, what we do, we heated our sample at elevated temperature to accelerate solid state diffusion. This is called homogenization. Right? So this process, heat treatment process, must be carried out at a temperature that is lower than the lowest melting solid in the alloy, or else melting will happen. Okay, what does this statement do? He say, if you want to do homogenizing heat treatment at temperature that is lower than lowest melting solid, lowest melting solid, let's say 30% copper, 30% copper, 70% nickel. What is the melting temperature? What is the melting temperature? This if you want to do this one, if you want to do 30% copper, what is the melting temperature? T1, T2, T3, T4, T5, T6, T7? What is the melting temperature? You want to do like normal treatment. So you go up there, this is solid, right? You increase temperature, increase here, still solid. Here you start to see liquid already. T5, around T5 lah. Because this line, you already start to see a little bit liquid come out already. This is a melting temperature. Okay. So what you do, you increase the temperature a little bit. Area temperature that is lower than the lowest temperature of the casting. So you do a little bit below there. So example, a temperature below T7. Let me see. T7. Okay, so this is the textbook. You choose T7. T7 here, below T7. Gibbs. If the alloy is overheat, localized melting or liquidization may take place. Okay. This is you do if you do heat treatment who carry out at T7 here and not here. Okay. You see, it depends on what you want. So if you want to do 30% rapid cooling process, you choose a temperature just below the T7. T7 for rapid cooling. Okay. Because you want to eliminate the waveform surface. So what you do, you just go down a little bit here. Okay. Okay. So if the liquid phase form a continuous film along the grain boundaries, the alloy will lose strength and may break up during subsequent working. So there is a grain boundaries. Grain boundary means the crystal when it become bigger and bigger crystal. So two crystal you will join together. So the melting process will start with the boundaries over here and here, like sweating lah. So when there's a sweating happen, then there's a liquid come out. So when liquid come out, the structure become weak already. It can slide each other, right? So it become weak already. Okay. So this is additional notes, additional notes. So okay, this is just the recall of how you do the rebel rules, right? So if you pick this one, then we give you B point. You should able to find how many percent of LOS and how many percent of solid and liquid lah. Okay, so if you use this portion, what is the percentage? Is it liquid or solid? If you use this section, percentage of liquid. If you use this compared to the overall rank, solid if you use this one, it's a percentage of solid Understand? Because this is liquid, this is solid it's the opposite one. Okay. So with that, you should able to understand the rest already. So let's see equivalent cooling and non-equilibrium. Non-equilibrium means rapid. So you know that the top red line is liquid, bottom red line is solid. So let's say we take 35% concentration and we draw a line here. Okay. So at A, in test, what should you draw? In A liquid, you just draw a bubble without nothing inside. You just write L. It's liquid. What you see under microscope is liquid. So you write 35% nickel. Okay, liquid with 35% nickel. Okay, or another component. But in this case, we look at nickel. So you can write 35% nickel. Okay, so then you drop down the temperature slowly, homogeneously. You reach this one, it become what? Liquid and chicken pox, and a small dot of particles come out already. Okay, so then you draw bubble, liquid, you just point to the empty space here, liquid, then you write 35% nickel. Then here is a chicken pox, right? Chicken pox is what? Is nickel solid. Nickel solid is alpha. So you write alpha nickel, but how you get 46%? At this line, you stop here. you pull to the right. Where does the chicken pox? Chicken pox is a solid particle, right? So how you know concentration become at this line, at this graph, this line tell you is solid, right? So at this temperature, you draw a line. At this temperature, you will form how many percent of nickel? 46. About there, you drop down, you get 46% nickel solid. Understand? So that's why this small chicken pox is consists of 46% nickel. Make sense, huh? Okay. So first, the next question coming out, you should able to understand and draw the diagram like liquid, how many percent of that component for this example, liquid 35% nickel, and the B point is 100% liquid with 35% nickel, and the chicken pox here, the particle solid metal here is 46% nickel alpha. You should write alpha bracket 46% nickel. How you know 46? You draw a line at this same temperature and go and touch the solid line. Then drop down, you'll get 1%. Okay. So this is 46% nickel. Then you further drop to point C. It become bigger and bigger because this one grow already and drop temperature become bigger and bigger chicken pox. But percentage of chicken pox is, you have to draw at this temperature, draw one line, go and see what is the solid concentration. 43. So you get 43% nickel alpha. Okay. But the liquid change already. The liquid is 32%. So you go to here. Go here. So here you can find the LOS. How many percent liquid, how many percent solid. So this one is solid, this one is liquid. Yeah. Okay. D is what? This is beacon chicken pox with 24% liquid, 35% nickel. Yeah. So then you further drop is 100% solid. You draw alpha, like a fish scale, like a cell unit. Then you write alpha 35% nickel. Okay, so this one you understand. Then we go to rapid cooling, which is non-homogeneous. So if you follow the line, let's say we rapid cool at the same percentage, 35%, right? So 35%. Now we rapid cool it. Rapid cool. So here is 100% liquid, but with 35% nickel. Drop to the first point here. Again, chicken pox come up with 46%. You drop down 46. Then you further drop here. Further drop here. Here you will see bigger chicken pox, but with a different layer here. Two layer. The first layer is this one, 46% one. This one. Okay. How you know is a rapid cooling? This is the original one. This dot slash line. So you will see like black color or red color. So here, this one, the dash line is the normal one, but this one is like string already. The room string already. No, not dotted line, but you go to the solid line. Like for example, this one. This one you understand, right? This one, how many percent of solid? You go to the end. Here you get 46. But you rapid cooling already. The rapid cooling red line bottom one already shift to the left already. So here to here, here is 40%. If you drop down, you see 40%. So the outer layer is 40% and not 42%. Here is 42 lah. It's not 42 ah. Okay, you must touch the line. Okay, rapid cooling, you surround with the early one. Outside at this temperature is also alpha, but different concentration. Then you further drop to D. To D, then you see the another layer already. D is this one, 38 lah, about 38 lah. No, sorry, 35, correct, 35. So you surround with one more, 35. You have to touch the red line, not the dash line. Yes. It's like how many stop, how many stop you have? One stop, you have one layer. First layer, second layer, third layer, fourth layer. Oh,
The normal.
this is the rapid cooling graph. This is rapid cooling graph.
Oh, so this is the dotted line is the
Dotted one is the left hand side one.
Okay.
It just show you that what happens when you do rapid cooling. The phase will shrink. The spring or it will like big lah, but the graph will tell you whether it's a rapid cooling or not. So what is the difference between normal cooling and rapid cooling? When you draw your answer, rapid cooling, you only see one type of the solid, one type, one concentration. But here, there's a layer by layer, okay, and different concentration. It depends on how many stop lah. In this case, it give you 1, 2, 3, 4, 5, 6 stops. But start to see chicken pox is station number 2. So you have the first layer at this concentration. Then you stop here. You should have second layer. But second layer, outer layer, you should see this point, 40%. So you have 2 layers, 40 and 46. 46 is inside, 40 is outside. Okay. But the liquid also change concentration. You see at another side. Because this liquid ma. Okay. No need. You just need to label what is the white color. What is the white color things lah. Okay. Then it drop down already. D is near to solid already. D is near to solid, but still have liquid. It still have liquid. Still have liquid. So the liquid is 24. And if the question asks you lah. Okay. If the question asks you. So there's a liquid. There's a liquid when you do rapid cooling. Then you drop down to E already. E is still have liquid.
Why still got liquid? It's not in the solid already.
No, although is in the solid. Which one? This one. This one is the normal one. Normal cooling, but yeah, so it's still got liquid because it's a rapid cooling. It's not enough to cool down. It like cool down too fast already. Like some still stuck at liquid form. So here, you rate the liquid at here lah. Okay. Solid, you have a few layer lah. So this first layer, second layer, the core, first layer, second layer, third layer. So the outside one you read here lah. For example, E outside layer is 31. Yeah. Although rapid cooling already inside the solid region, but still have liquid.
But wait, this is the rapid cooling line.
This graph is for rapid cooling.
So if I extend this from here to here, actually this is liquid lah.
No, liquid is over here.
I mean, sorry, solid liquid. Solid liquid will be over inside here lah.
Normal one.
Normal one.
Here to here is normal.
Okay.
But now you do rapid cooling.
Oh, okay.
Rapid cooling is here. Rapid cooling is rapid cooling is the solid line here.
Okay.
Which one? This one? Yeah. This one, for rapid cooling, for non-equilibrium is very hard to find using the level rules because it's a mixture of layer. You can only like qualitatively guess what is inside. If you cut open the particles, the chicken pox, you cut open, you'll see like a few layer inside. But how many percent is very hard to, how many percent of liquid and solid is very hard to guess. Yeah, you just write, for example, here, you understand the percentage, right? All this percentage, right? So when you come to E, you read liquid is here, solid is here. So solid is 31%. The most outer layer is here. Then the rest outside is liquid. But the particle size is bigger and bigger already. It's like the concentration. You can only guess concentration, but you cannot guess how many percent liquid, how many percent solid. You can only guess the percentage of concentration. E, this one. Yeah, E, you just read here and here. Liquid and solid. The rest outside here is liquid. The liquid form here. All right. Although you already enter into solid, but because you rapid cooling, you still have seawater inside, the liquid form inside. Okay, when it reach F means already everything is solid already. So you have the normal liquid, but the percentage still remains same as the previous one. Okay. So here F, you have 46, 40, 35, 31. No more liquid. Means the outside layer, this one, just now E, you have 31% of alpha. So 31% of alpha, this pink color things will grow. It will grow and fill in the liquid. Yeah. So this is a bit challenging for the non-equilibrium one. This one. This one. This one. Yes. Another is another layer, but it's the same composition. Means the 31% expand outside. This means this color changed to 31% alpha. Yeah. Okay. Now we already finished with the nickel copper. Now we look at lead and tin system. All right. So they have a limited solid solubility. For example, this graph. So before that, you should able to identify axis first, temperature, Celsius, and the composition. Composition, this is binary system. You have two items inside, PB and SN. Okay, PB and SN. So you know that on the left hand side is 100% PB, right hand side is 100% SN or tin. Okay, of course in exam, if you're not able to understand which one is tin, you just read the graph title or caption. If it tell you this is what percentage of tin, the far right is tin. So tin is SN. Okay. Now, by having said that, once you identify the axis, then you look at the line and look at the boundaries. So on the top, you know that your temperature very high. On the top here, you will see liquid. Okay. So liquid, then you will see alpha plus liquid. This one beta plus liquid. Beta is a solid lah. Okay, then this one alpha and beta solid. On the left hand side also solid, but it's the alpha solid. Two different material, but different like ferrum, you have alpha ferrum, gamma ferrum, alpha ferrum, right? Same with the tin. Sn also have alpha, beta, but they are solid. It's like different team lah, different member like that. Okay. But what is important, you know where is solid, where is liquid, right? So here, below here, sure you know it's solid already. Alpha is a solid, beta is a solid. So only you need to identify which one is alpha, which one is beta, at what temperature it become alpha, at what temperature it become beta. Okay. So previously you learned about triple point, right? How many triple point you have on this graph? Or more than triple point? Triple point or 4 point?
One.
Here is triple point. At this point means that you have zero freedom. So here you don't, I mean here you have, at this point, you have alpha liquid and alpha plus beta component here. Here you have a lot. You have this one, this one, this one, and this one. Okay. This one also. This one you have beta liquid, beta, and alpha beta. Okay. Here, what is this? Here is liquid. This one is liquid. This point. Because this one is high temperature already. Liquid. But drop a little bit, become, you will see solid, alpha liquid, and alpha. But of course you say, sir, can this point be alpha? Okay, because at this point it touch liquid, it touch alpha liquid, it touch alpha. Okay, here you don't know. Okay, most right. This one where beta liquid. This one. This one you see liquid, and you might see beta liquid and beta. Okay. This point, okay, this point is melting point for beta. This point is melting point for beta, because you start to see beta already, right? This point is 100% solid beta. But what is important is the melting point of beta. What is the melting point of alpha? Melting point alpha, this one, because you start to see alpha this point. What else? Yeah, the rest is, I think you already expert already. Okay. So the next one is to introduce you a few technical words. For example, eutectic, protectic. Okay. What is eutectic? What is protectic? Okay. Okay. So if you're given this kind of graph, use back the word. For example, you see liquid. This is liquidus, solidus, solvus. You just use back the word. This one. Okay, I'm going to explain that one. Okay. So this is equilibrium phase diagram, means you cool down the object slowly and not rapid cooling. Okay. Okay. So diagram characterized by limited solid solubility in each terminal phase is either alpha or beta. Okay. So the eutectic invariant reaction is at 61.9% Xn and 183 degrees C is the most important feature of this system. The eutectic point, alpha and beta. Okay, so here we slowly dissect. So here 61.7.9 is the one that you see alpha and beta liquid at this point. At this point, you'll see two types of solid, alpha and beta at the same time. At this point. This point, when you see two types of alpha together with the liquid, is called eutectic point. When you see two kind of chickenpox together in the liquid form, in the liquid, you see two kind of chickenpox, they call eutectic point. Yeah, correct. Two kind of like crystal, like two kind of chickenpox species inside the water. Then it's called eutectic point. Okay, so you should able to identify where is a eutectic point from today onwards. Even you change the graph, but you look at the graph when there's a point that you see two kinds of chickenpox in the liquid environment, then there's a eutectic. Then you should able to identify what is the concentration or what is the concentration of component at the eutectic point. In this case, you drop down, you see 61.9% of Sn and 38.1 PB at this point. Then at what temperature? You extend this one to 183. This is an important point. So the question will ask you, where is the eutectic point? Eutectic point happen at concentration of 61.9% Sn or dash 38.1% PB at temperature 183 degrees C. So it's like you're reading a map. Okay. So okay. So at that point, at eutectic point, how many percent of alpha and beta you have? I give you the answer. Are you able to see the logic of this answer? At eutectic point, you will get 19.2% alpha. How you know 90% of alpha? You extend this one, you will see alpha, right? Drop down, you get 19.2% alpha at eutectic point. And how many percent of beta? Drop down, 97.5% beta of Sn, and liquid 61.9% Sn can be coexist. Yeah, so at eutectic point, you see two species in the liquid. So you need to say how many percent of species 1, how many percent species 2, how many percent liquid. In this case, at eutectic point, alpha is at this point, beta at this point, liquid, you read the percentage. Yeah, so this is 3 important answer. Each one it will cost you like 2 marks to mention this one. Okay. Yeah, about there so you say like identify eutectic point on the graph. So you say where is it, what temperature, at what concentration, right? So this is 1 point, and then at this point, how many what do you see at this point? How many percent alpha? How many percent beta? How many percent liquid? How many concentration of that? Okay. Okay. Yeah. No, it will mention very specifically identify eutectic point. So eutectic point where? At what temperature? At what concentration? Yeah, you might on your the graph. Then you mention temperature. You mention the percentage of the, in this case, 61.9% SN. Okay. Then at that point, what do you see? What are the member inside? Alpha at what concentration? Beta at what concentration? Liquid at what concentration? Yes, yes. Just go down from here. Just go down from here because here is the liquid form. Go here. Okay. Okay. Then another one, introduction to that one is called terminal solid solution. What is terminal? Terminal is the left hand side, right hand side. So you have a eutectic point. Your terminal is on the left and on the right. Okay, so it's either beta phase or alpha phase on the eutectic point line, left and right. We call it terminal solid solution. Okay, you will see. Okay, the question might ask you, what can you found and at terminal solid at the terminal at the terminal point of A B diagram. So you go to the diagram, go and find eutectic point. Then go and find what is this, alpha and beta. Okay. You're going to see what the question will ask you at terminal point. What do you see? What do we have? No, eutectic is here. Where's terminal? Both end. Both end where you see solid. The question asks you what solid you have. Alpha solid and beta solid. The answer is alpha solid and beta solid. Alpha at the left, beta at the right. Okay. Okay. So alpha phase is lead rich solid and can dissolve in solid solution a maximum of 19.2% SN at 183 degrees C. You should be able to understand this statement. So let's see alpha. Maximum solubility of your SN is 19.2%. Means you're able to dissolve your SN or your tin is 19.2% only at this point. Okay, at 183 degrees C. Okay. Wait percent. This one concentration. The one we learned in chapter 2. Chapter 2 or chapter 3. Okay. All right. Then beta phase. Beta phase is a thin rich solid solution. Solubility is 97% SN and is 2.5% PB. 2.5% PB at 183 degrees C. Okay. You just drop down and see what is the maximum you can fit in. Just don't confuse between the two member here. Don't confuse between the left and right component. It can be thin, it can be PB. It can ask you like how many percent of solubility of PB at the eutectic point at this temperature. Okay, so it can be this side, it can be this side. Mm. Mm. Correct. Yeah. Yeah. Here, lo. Yeah. So here is alpha. So maximum alpha phase solute you can dissolve SN is 90.2%. if you want to get alpha. You want to get beta, you maintain at this temperature, you put in 97.5% of SN is still can dissolve if you want to get beta. But you cannot get alpha. Alpha very low, low thin. Beta rich thin. Yes. Okay. So you need to identify at what scenario I get what. Okay. Okay. Another one is just add-on information. There's nothing complex here. Okay. It's just I think you can understand what is the diagram. So this is on the left hand side. You know that this is alpha solid. So if you drop down like the main purpose showing this one is that we expect you know how to draw the bubble here. I mean what do you see at this location? This 100% liquid. All right. So C1 concentration of your SN. So at here you read the SN, the concentration here. Then you drop down. You drop down here already, you start to see some alpha appearing there. Then here, full solid alpha. You drop down here, also alpha, and so on. Okay. So the rest you read lah is what is I want to highlight is when there's a different species like alpha, beta, you better label carefully lah in your diagram. If the region is alpha, beta in the solid form, you just label accordingly lah. So this one is alpha, this one is beta. Beta is another species lah. Under microscope, you'll see different texture. So alpha is on the left one. The species alpha. Beta is another side. This is a enlargement of this diagram. Yeah. You just it depends on the region where you fall down, where you fall or pinpoint. Okay, if you're at this region, you know it's alpha lah. Like for example, I pinpoint here, it's alpha. Then I drop down, I pinpoint here, it's alpha plus beta. Okay. Okay. So here, like here, you use a different pattern. Example, this here, you have alpha, beta together. So you have eutectic alpha, eutectic beta. Here. You draw different contour, then you label beta, alpha in eutectic point. So here, the pro-eutectic, pro means before the eutectic point. Sorry, a pro means is towards the alpha. Pro means is towards the alpha. So it's on the left. So it's a pro-eutectic of alpha. You'll get alpha here, right? So it's a pro-eutectic. Okay, pro-eutectic. Okay, and so on. Yeah, so you should able understand why this one got pro and eutectic. Because this one already come to the E, already come to solid already. Okay, go very fast. The rest you read. Okay, you should already identify where is the eutectic point at a certain temperature and so on. Okay, then okay. Now again, just want to highlight like at this point you know is alpha solid, alpha beta, right? At this point. Important is that you know how to write the percentage of alpha and beta. For example, at this point. So you go left, right lah. It means you drop from here, then you cool down already, it cannot, the percentage stuck at there. You cool down solid. So here you get 13.3 alpha, 97.8 beta. Okay. Okay. So the equation is important for chapter 9. The question will ask you to write eutectic reaction. Eutectic reaction, you know that what is eutectic, right? Two different species of chickenpox. Is must be from something, right? Liquid to become the two chickenpox, right? So you write liquid, arrow, alpha, beta, solid solution. Then you write cooling. You need to be cooling. Then you write eutectic temperature. In this case, 183. This is a formula. The formula. Okay. I try to conclude this one maybe another 10 minutes. Then we break lah. Then we end the class lah. Okay. So this one is eutectic reaction. Means eutectic means you see two different species. So it must be cooled down from a liquid. So liquid arrow. Remember to write this one. And alpha beta solid solution. So this is just a highlight lah. In eutectic reaction, three phases coexist. Mean you see liquid, you see alpha, you see beta. Okay. And at this one, if you use the grid rules, the freedom is 0. Okay, the freedom is 0. So here is the horizontal thermal arrest. Okay. Now we start to do analysis. Consider alloy 1 of eutectic composition, 61.9 SN. You cool down from 200 degrees C to room temperature. 200 is from here. You drop down to here. So you see what happened. During cooling period, 200 to 183, alloy remain liquid. So you need to know how to explain. This is the steps. Like at what temperature, what do you see? And then at another temperature, what do you see? So 200 to eutectic point, you see liquid. At 183, you get eutectic reaction. You write the eutectic equation. Liquid become alpha beta solid solution temperature. You write this one. Okay. So this one you write how many percent of member 1 the liquid, then how many percent of A and B. Okay. So upon cooling the alloy from 183 to room temperature, there is a decrease in solid solubility of solute in alpha and beta, the Solvius line, this one. So if you drop down this one, you will see left hand side and right hand side Solvius. Okay, you drop down, you'll see left hand side, right hand side. Okay. This is solubility. So again, I highlight. So diffusion is low at low temperature. This process does not normally reach equilibrium. So it's below eutectic temperature. So the question sometimes does mention below eutectic temperature, then ask you explain what happened to the alloy, right? The solid solution alpha still can be differentiated at room temperature. You will see something like this under microscope lah. You see something like this, different alpha, different beta. Okay. Now on the right hand side of the eutectic point, we call it hyper eutectic. On the right, we call it hyper eutectic. On the left hand side, we call it hypo eutectic. So if the question mentioned, ask you to find something on the right hand side, it will not mention right hand side of the eutectic. It will ask you to go hyper eutectic area, go and find something. Then if you want you to look at the left hand side of eutectic, it will use hyper eutectic area. So you need to look at the left hand side. Yeah. So the rest is you read lah. Huh? Nothing is already explained already. Okay, so the question normally come out, it give you 1%, for example, the line that you see with A, B, C, D, then it asks you to assess at what temperature you start to see alpha, at what temperature you start to see beta, and so on. Just read from the graph lah, right? This one you read lah, I have everything there. Okay. Right. Now here is alpha liquid, right? And as you drop temperature, you start to see liquid and beta already. Okay. So eutectic reaction again, liquid to alpha beta. Okay, the rest is also illustration of what happened to that line. Again, the purpose of showing you this is that we expect you to know how to draw the bubbles. What is inside the bubbles? What do you see under microscope? Okay. So eutectic structure, primary, alpha, and beta, and eutectic alpha. Okay. So this is additional material. This is CuAg. Again, go and read the graph caption. This is Ag, so right hand side is Ag. Focus on Ag rather than another side so that you don't confuse with the graph. So are you able to identify eutectic point?
Yes.
Where is it? At E point, yeah? So concentration of 71.9% of Ag at what temperature? 779, give you already, okay. So then you have alpha, beta also, and so on. Okay. So this one, another one, PBSN. Also, you should know where is eutectic, 7.98183. Where is the hyper eutectic? This side is what? Hyper. This one hypo, okay. So this one is the reaction that you have various morphologies. Morpho is a change. Morpho means change. Logis is shape. So you have different kind of shape in alloy. So you can see lah, ABCD lah. So you have like layer cakes, one layer by one layer. Growth direction from the far to the front. Second one is rod shape. Third one, I don't know, like a small dot there. Then the D one is got a needle shape. Okay, so these are the few interface that you have. So various eutectic structure is called eutectic structure. Again, eutectic is the one that you make from liquid to become alpha and beta, or two different species. So you have laminar, rod-right, globular, and acicular. So these are the four structures lah. So you see this one under microscope. Okay. Okay, let's go to example 4. Then we call it a day. Okay, just a practice lah. Huh? So to understand whether you understand or not. Let's say you look at this diagram, right? Of course, in the test, you won't see all these lah. We will remove all these. Just give you the blue line. Okay, and alpha, beta, and so on. So make phase analysis of equilibrium, solidification of lead tin alloy. So go to the graph caption there. This one is tin. So right hand side is tin, right? So following the point or diagram figure at eutectic composition just below 183. Just below 183 here. Okay. So the point C, I asked you to do analysis, means how many percent of eutectic, how many percent protetic, and so on. So I show you, okay, I show you, the first one. At eutectic composition just below 183, what do you have or what do you see over there? Okay, so at this point, just below 183, alpha, beta, solid, right? So phase present is alpha and beta. This is a working that we expected in your answer sheet. So you write phase present. What do you see? Normally have two or three. So in this case, got 2. You will see alpha and beta here. Composition of phrases. Composition of phrases, you read from this line. So here, 19.2 alpha, 97.5 beta. So you write like this. Okay, so you write phase present. What do you see? Composition, you read from the graph, 19.2, 97.5. Bracket alpha and beta. Okay, the third one, amount. You need to calculate a little bit. Amount, you already know the level rules, right? This one is the opposite one. Here to here, mean the total length is here lah. If you calculate this to this, you find beta. This to this, you find alpha. Same level rules. The equation is direct. So to find alpha, actually it's here to here. So you take 95.5 minus 61.9 divided by the total length times 100%. Alpha, you get 45.5. B, you can do the same procedure or you can straight away take 100% minus this one. You get 55.5%, 54.5%. Okay? So you got marks on, this one at least 2, 2, 2, and 2. So here about 10 marks already. So you ask you like, it depends on complexity. So it's normally like here, if I very generous, you can at least have 10 marks here. 10 or 5 marks. So what 1, 2, 3, 4, 5 lah. Because it got like A, B, C, D. So like about there lah. About there. So this is very easy to score. So B, he asks you what happened at 40% SN and 200 degrees C, 230 degrees C. You need to go to the graph and look at 40%. Is here. Go out and then 200 degrees, 230 degrees C is about here lah. So same procedure. You write, what do you see? What do you see? You draw a line. Okay, you draw a line. Present phrases. What do you see? Liquid and alpha. Yeah. Then second one is composition. How many percent liquid? You know this one, right? LOS, right? You know this one. This one is S. This one O. This one L. So you calculate this one become liquid. This one is solid. Right. Go back. Here, composition, you read from the graph lah. Composition, 48. liquid, this one solid lah. This one is the part that you was confused. If we change the graph, you will confuse, why suddenly this one solid, this one liquid? But this one you read from the graph. Because you know alpha is solid, beta is solid, and so on. So this one you read from the graph. Then the next one is to calculate the percentage of phrases. Percentage of phrases, you use level rules. So this to here, this one to here, you calculate what? Liquid. This one to this one, you calculate solid alpha. So same. Okay. The same working, maybe 4 marks, right? And so on. Then number C. C is eutectic plus delta T. Means you heated above. You see the question got plus delta T. It means above the eutectic point. Above the eutectic point. Okay. The same line, 40%. But above eutectic point. Or sometimes the question will not directly like this one. You will change this one to eutectic temperature or eutectic point temperature plus delta T, or just above the eutectic temperature. Okay, so in this case it's 183 plus, so what do you see? Just above, what do you see? Alpha plus liquid. So same lah. Same thing only, but just the percentage a bit different because you read from the different line. Okay, so 61 about here, 19.2, that one. Then calculation still same, level rules, LOS, level rules same. Then negative means below. E point lah. Beta. So liquid and alpha. Sorry. Oh, this is I think it's wrong. No, it's wrong. It is the wrong answer. You see the correction? This is the wrong answer. It's not liquid and alpha. It should be what? It should be alpha and beta. Okay, it's not liquid alpha. It's not liquid and alpha, but it's alpha and beta. I just purposely put wrong one, but just to do correction for you. Okay, so it's not, it's 19.2% and 97% beta. Then you do the calculation. Okay. Okay, this one, example 5, go and read. Okay, your homework. Go and read. Okay. Next class, we will look at this one. Actually, it's same concept. It just want to show you like different material only. The same concept like level rules, what is the phrase, and so on. Okay. The rest you read lah. I think you understand this one. Right? It's just that you look at the graph, like what do you have? Like delta, gamma, beta. Can you identify where is the eutectic? It's C point. Then what is it? What? Yes, terminal point. Correct. So this is called terminal with a delta. Okay. Then yeah, the rest is you able to read already. Okay. So this is hypo. Sorry, hyper. Okay. Hyper-eutectic. Yeah, the rest you know how to read already lah. Then the melting temperature of delta. What is the melting temperature of this one? This one, okay lah. The rest you know already. Then I can skip this one. It's just different process. That's all, right? So it's just like, for example, this line is it tell you you got two species here. You have gamma and delta at here. So here you know what is this already, right? No, this one between these two space. Between these two space is what? This one. You don't have delta yet. You don't have gamma yet. This one is delta plus something. Delta plus is a delta plus. Delta plus something. Delta plus liquid. I think so. But this one, this one, delta is here. Sure have delta. Here sure have delta. This one is gamma. Oh, I think this one is no. I think this space here is gamma plus delta. This space gamma plus delta. Then after the blue one is gamma. Okay. Okay lah. The rest you read lah. This one is like at what you got FCC, BCC, and so on. Nothing that one. Okay. But of course, in test we won't ask you like alpha, delta, they in what this one. We won't ask you that. Okay, paritatic and so on. So paritatic, paritatic one equation. Just now you learn about eutatic. Paritatic is liquid plus solid become another species. Here. Okay. Paritatic is liquid plus species 1 becomes species 2. It's called pari. Yeah? Pari, liquid plus species 1 on the left, liquid plus species on the left, it transform into the one terminal point at the right. This one. Okay, it's called paritatic. In this case, 175 and so on. So paritatic. The rest same, you read. Paritatic point C. Okay, just now, early, when we come into this graph, we say that C is a eutatic, right? So it's wrong, it's not eutatic, but it's a paritatic because it's from, it joined from this one, this side is a gamma already. So it's from liquid, join with liquid, this one, this here is liquid, liquid delta become gamma. Okay. Okay, this one you read. As long as liquid plus species 1 becomes species 2 is a paritatic. The one that I highlight is called what? All right, just highlight what happened in that particular things. Okay, this one you read. Okay, so it just if alloy have less than 34.3% nickel, less than this one, it slowly cool from liquid states through the liquid plus gamma delta region. There will be excess of delta phase after paritatic reaction is completed. Okay. So here means there is a excess of paritatic. Okay, so this is another complicated graph compared to the one that you see. So here you have to identify where is the paritatic region. Paritatic again, liquid plus species A becomes species 2. You need to read carefully from the graph. Okay. Okay. So this one, paritatic. This one you read from the graph. So same layer by layer, paritatics. Yeah, paritatics. Alpha plus beta become beta. Beta will surround it will cover the earlier alpha. So when you see the word encapsulation or encasement is a rapid cooling, non-equilibrium phenomenon. Okay, the rest you read. Read. You'll see something like this on the under microscope. Okay. Then example 6, we'll look in this one also homework. Go and read. Okay, example 6. Okay, we will continue monothetic next lecture. Okay, we stop here. We stop here. We stop here.